So far in this class, we've been working with one-dimensional motion or straight line motion. And so we're going to turn a corner today with this screencast and start talking about planar motion. And this means that we need to become more systematic in how we create our models. And so when we create our models, we're actually creating system models because they're composed of multiple individual elements. And it's these individual elements that we can apply Newton's laws to if they have mass. So let's start by taking a look at the step-by-step list for model creation. So we have 5 major steps, and we're already doing some of this. First, it's to sketch the system. And that's important because we need to take a physical system and then create what our representation is on paper with all the important elements. Then we identify the reference frame or reference frames. So far we've been working only within an inertial reference frame, but that's going to change as we become more complex with our tools. Next, we annotate the direction of gravity in the problem. This is an important step simply because not all problems have gravity. You need to make a decision as to how the object is moving, whether gravity matters, and if that's the case, draw that with an arrow in its direction. And then fourth, this is one of our major steps that you'll see, is that we identify the coordinates needed to fully describe the motion and identify the kinematic constraints. We've been applying coordinates to our problems so far, and in straight line motion, that's a pretty easy task. And so we've been able to just say positive x, positive y, negative y. But when we get into planar motion, we need to be clever sometimes about how we identify the coordinates. You'll find that there's no one right answer. There are multiple answers. Some are better than others, meaning that some are easier to use. And then by identifying the kinematic constraints, that's where we're actually creating constraint equations that help us understand the motion of the system. And then finally, we make it to something that you've been doing for a long time now, and that's creating free body diagrams of each component with mass. So we'll split up the entire system into multiple parts that each have mass, and we apply Newton's second law to each of those pieces. So let's take a well-known system, the Flyball governor, and let's apply this systematic process for developing our system model to this particular system. And what a Flyball governor is it's a simple mechanical controls mechanism in which we have 3 masses. We have 2 masses that are our centripetal masses, and then we have a mass at the bottom. And when this spins due to an engine spinning, then we see that our fly balls will swing out, and then it's going to change the position of this mass, which is attached to a lever, which is going to open and close a throttle to then govern the speed of the engine. So let's watch this short video, and you'll see the flyball governor in action. You can see as it begins to spin, you see the masses move out due to centripetal force. And then you can see this collar on the middle that's going up with higher speed and down with lower speed. As we said, that's connected to the throttle, and it'll regulate the speed of the engine through that mechanism in the throttle. So it's a controls mechanism in that there's a feedback loop that's occurring there that's regulating the speed. So let's step through our process and create a system model of the flyball governor. The first step is to sketch the system. So let's start by drawing the line of action right in the middle of the flyball governor. And at the bottom of this, we have the collar, which we'll call point C. And then out to the side, we have each of our fly balls. And this is going to be a simple model, so we're going to make it symmetric. In between C and each of our masses, we're going to draw a straight line in which these are massless rods that pivot. We'll call this point A and then point B. And then our origin will be at the top. There's where our O will be. There's a pivot there, and then a massless rod that connects O to A and then O to B. Along the line of action in the middle, we have a spring which is attached to a hard stop. So as the collar moves up, it'll have a hard stop and we'll compress that spring as it moves up. And then we have some dimensions that we need to put onto the system. Each of the rods that connect OA, OB, CB, and CA are all the same length in this model, so we'll call it length L for each of these. And then the next thing that we need to identify are the masses themselves. So we'll say that the fly balls have mass M, and they're the same. And then the collar has mass big M, so it's a different mass. Next we need to define the spring constant K, and then it also has a resting length of Y naught. And this takes us to step 2, which is to identify the reference frames. So far in this class, we've only been concerned with an inertial reference frame, and we're going to continue that in this problem because we're only going to be concerned with the motion in the plane that's defined by OACB, because we're not going to concern ourselves with how it's spinning. If we did that, that's three-dimensional motion, and we certainly need more than one reference frame. So apply the inertial reference frame here, and that frame I is defined with an origin at point O, and then the basis vectors EX, EY, and EZ. So we'll go ahead and define the vectors for this problem, and we'll get in the habit of doing that as we work through this next chapter. And these vectors themselves are going to be in, we'll say EX is a unit vector pointing in our view to the right, and then EY pointing from how we're seeing this down. And then EZ is going to be the cross product of EX into EY. So that means that EZ is going to be pointing into the page, and a vector that's pointing into the page, we make an X as it's moving away from us, and then that indicates that EZ is going into the page. So we'll always define each of these three vectors that are defining the reference frame. In step 3, we annotate the direction of gravity, and in this problem, gravity is in the direction of EY. So make an arrow and put a G by it, so that's a reminder to always consider that gravity is acting on those masses in that direction. And now we move to step 4, which is to define the coordinates and constraints. And this is one that we'll have to stop for a moment and think about. We need to have a coordinate for every degree of freedom that's in our system. And so we'll define an equation that links the number of degrees of freedom in the system with the number of particles and the number of constraint equations. And that's defined by m is equal to 3 times n minus k. And this is where m is the number of degrees of freedom in the system. The coefficient 3 is the potential degrees of freedom per mass in the system. N is the number of masses in the system. And then K is the number of constraint equations that we have that reduces the potential degrees of freedom to the number of actual degrees of freedom. Now one thing to notice here is that we're using the number 3 for the potential degrees of freedom per mass. And what that's saying is that we have 3, we live in three-dimensional Euclidean space, and so each mass can translate in 3 dimensions. We typically think in the x direction, y direction, and then z direction. But in this class, we're not dealing with three-dimensional motion, so when we use this equation that relates our degrees of freedom to our constraints and number of masses, we're going to use the number 2 here because we only have 2 potential degrees of freedom per mass. So let's write this equation for our flyball governor system, and we'll start on the right-hand side of the equal sign. So we have 2 potential degrees of freedom, and then we have 3 masses. And then we still need to determine values for K and then for M. So we've got 2 approaches we can take. We can either try to find K, which is developing all the constraint equations systematically, or we can look at our system and intuit the number of degrees of freedom and then decide how many constraint equations we need to go find. Most of the time, we're going to do the latter, which is we're going to look at the system, decide how many degrees of freedom are there, and then go searching for the constraint equations. So let's go back up, and then as we look at this system, hopefully you can see that what we're looking at here is really a 4-bar linkage we've got each of these bars of length L, and then C is sliding along this direction. And so all the motion of each particle is constrained to each other, so this is actually a 1 degree of freedom system. So let's go back to where we started, and that's where we said we're defining coordinates, and we need to have one coordinate for every degree of freedom that's in the system. So if this is a 1 degree of freedom system, then we need to have a single coordinate. And that coordinate that we're going to use in this problem is theta. So as theta gets bigger, then we see that the collar moves up. We see that each of these fly balls move out. As theta moves towards 0, we see that the collar goes down. When theta is 0, the collar is the lowest that it can be, and then the fly balls go down with decreasing theta. So the whole system and the motion of the system is constrained to the value of theta. So let's plug this into our equation now. And we know that it's a 1 degree of freedom system, and so if m is equal to 1, now we've got minus k. So 6 minus k is equal to 1, and that means that we need to find 5 constraint equations. Now what these constraint equations are doing is they're going to relate the positions of each of these masses, so A, B, and C, individually to the point O using theta. And so what we'll do is we'll consider the geometry of this 4-bar mechanism individually for each mass. So let's start by sketching the triangle OAC from the left side of the mechanism. It's an isosceles triangle because we have the same lengths on each of these legs, and then we have the same angle theta at each of these angles. And we're relating each of these points A and C to the origin of the inertial reference frame. So let's dimension each of these points. Here we see that A is a distance YA in this direction, and then a distance XA in that direction, and then C has no offset in the horizontal direction, but does have the distance YC. And so we relate theta to these new dimensions in that YA is equal to L times cosine theta. XA is equal to negative L sine theta because this direction is in the negative direction according to our reference frame. And then we have the relationship in which YC, this larger dimension, is equal to 2 times YA, or 2L cosine theta, because we want to relate that to theta. And so with this single side of the mechanism, we've come up with 3 constraint equations that help define the kinematics of the system. And when we draw the triangle OBC, which represents the right-hand side of the mechanism, we get 2 more constraint equations. Y sub b is equal to L cosine theta, and then XB is L sine theta. And so in total, we have 5 constraint equations that we can apply that help us relate, recall what we're after here, that help us relate the positions of the masses at A, C, and B to position O using our coordinate that we've chosen for our 1 degree of freedom system, which is theta. And now our last step in creating the system model is to create free body diagrams for all the masses. So we'll start this process by sketching each of the masses. And let's start sketching our forces. We know that the force due to gravity is acting on each of these masses, so we have an mg, mg, and then big mg for our collar. And each of the massless rods applies a tension for each of the directions. And recall, just like in statics, we need to have equal and opposite directions for the arrows in which we have the same forces along the members. Go ahead and add your coordinates to these plots as well so that we know the dimensions. We have one more force to add, and that's our spring force that's acting at point C, F sub S. Recall that we're going to draw this in the direction that starts at the attachment point and goes to the mass, and our spring model is F sub S is equal to negative K, and then it's Y minus Y naught. And our Y in this situation is the Y of point C, so it's YC. We created a constraint equation earlier where YC is equal to 2 times L cosine theta. So you're able to take all this information, apply the constraint equations, apply Newton's second law, and be able to get the equations of motion for each of these masses. And so in summary, we have a 5-step process to be able to create a system model. And this is going to work for any system. Memorize these or write them down so that you do the same thing every single time. And if you do follow these steps, you won't forget any key elements, and you'll be able to set yourself up well to solve these future problems.